Okay, good morning, everyone. Let's get started. So today we continue to talk about database systems. So specifically, right, so you have database system contains your data stored as relation. If you are using a relational database, you as a user, right, create a table and the database system reflect that on your hard drive. And whenever you want information from your database system, right, you ask a query. Right? We talk about different ways you can write down a query. And then what's going to happen is database is going to bring the information all the way from the hard drive to you as a user. So starting from last week, we start to open up this black box, right? We kind of talk about different layers that database system has in like to enable this functionality. So specifically, right, from the top to the bottom, right, at the top, there is the SQL query that you are asking as a user, right? And you are hoping the database system return you the result, which itself is a relation. In the bottom, right, you have a whole bunch of files stored on your hard drive, and each file corresponding to some relations, maybe multiple files correspond to one relation, depending on which. But the bottom line is relations are stored as files on your hard drive. And then the first layer of abstraction the database tries to provide to you is a disk manager, right? And then you have the buffer manager, and then we have a whole bunch of access method. You have the whole bunch of relational algebra operators, and then you have your query optimizer. So at the bottom, the disk manager, right? So we talked about it last week. So the job of the disk manager is really try to take care of all the interactions with the hard drive. For example, allocate pages, delete pages, fetch pages to make sure all the pages, some of the pages are kind of stored in the same memory space, right? To make sure if you scan them, you have sequential access, for example. So the goal is really try to make sure everyone above it will not interact with the disk by themselves. Instead, whenever they want something on the hard drive, they talk to the disk manager. And then we move one layer up on Wednesday, right? So essentially, we talk about the buffer management. So the goal of a buffer manager is to give everything else, the upper layer, an illusion that your data is in memory, not on hard drive. So essentially, the abstraction provided to all the upper layer is to allow them to fetch a page, to update the page, so on and so forth. How does this do it? Essentially, it's going to maintain an in-memory buffer in the DRAM. Right here, you have 2 pages in the in-memory buffer. And whenever some upper layer tell the buffer manager, say, okay, give me the yellow page, the buffer manager is going to check whether this yellow page is in the buffer or not. If it's not in the buffer, it's going to fetch it for the user. Sorry, for the upper layer, not necessarily the user. And in this example, right, one key design decision you need to make is when the buffer is full and you need to fetch a new page into the buffer, you need to evict some pages, right? So here, hypothetically, if the buffer might decide to say, okay, I will evict the orange one, right? So it's going to push the orange one back to the hard drive and then bring the yellow page from the hard drive to the in-memory buffer and return the slot of the yellow page back to the upper layer. So this is a very simple interaction the buffer manager enables for the upper layer. And as you can see, if I am the upper layer, I have no idea whether the page I'm fetching is in memory or on hard drive. I can always assume safely all the pages are at least in my in-memory buffer, and I can do whatever I want as if they are in memory. Okay. And then we move one layer up and we talk about a whole bunch of access methods, right? So essentially, it tries to provide different ways of accessing data from a relation. You can do sequential scan on your relation. Last Wednesday, this Wednesday we talk about B-tree index, right? So today we are going to talk about the hash table, right? So all of this is going to provide different ways you can access information from the relation. So the interface it provides the upper layer is really all these higher level abstractions to access information on the table without interacting with the buffer or without interacting with the hard drive, without parsing the tuple by itself, for example. So sorry. Okay. So essentially, when you have your relation, right, you're going to reflect that on your hard drive as a collection of pages. And through buffer manager, I have the illusion that all these pages are in my main memory. And to implement some access method, right, essentially you need to have a sequence of invocations to the buffer manager, and then you write your access information in your relation. And then that's how you implement an access method. We talk about different ways you can access information. The simplest way is actually a very popular used way is sequential scan, right? So assuming you want to implement an access method whose semantic to say, okay, you have relation. I want to find a tuple whose attribute x equals to y. So if you want to implement this, you can implement it as sequential scan. That is, you bring the first page from the hard drive to the memory buffer. You scan all the tuples in that page. You check for each tuple whether their x attribute equals to y. If you find one, you return. You can bring the second page, you bring the third page, so on and so forth. So what is the cost here, right? So essentially, if you are assuming all those pages are stored together, that is, your scan is really your kind of like sequential scan will only require sequential access on your hard drive, right? So essentially, in that case, you need to pay 1 unit of seek and rotate time to really find the kind of essentially the beginning of the file, and then you need to pay d, assuming d is number of pages, d units of transfer time. For each one, you are bringing those pages from hard drive to the memory buffer. When the pages are randomly allocated for some reason, right? So it become more expensive, right? You need to pay d units of seek and rotate time because it's random access, and you need to pay d units of transfer time. And also, of course, you can also update tuples during the scan, right? When you do that, you need to write back the updates, so you will pay 1 more unit of transfer time. So the question that we want to understand is, can we do better compared with sequential scan, right? Because when you have terabyte of data, scanning them is often very, very slow. We talk about one way to do that. So we talk about B+tree on Wednesday, right? So essentially, it is a m-way search tree you build over your relation. So it's perfectly balanced. The way that it enforces that is it's going to enforce that every single inner node in the tree, other than the root, need to be at least half full. Okay, so you cannot have one inner node that is almost empty, right? So an every inner node is going to store a set of keys. When it stores k keys, it has k+1 children, right? And every single node is a page. So as you can see, compared with the binary search tree that you learned maybe in your first year, right? So B+tree is really designed for block access storage, right? When you have hard drive, every single time I access a piece of data, you bring me a whole page, right? So that is why in B+tree, every single node in the tree is a page, okay? And then there are multiple design decisions you can make. For example, you can have unclustered B+tree, where for every single leaf node, you contains the tuple ID, right, which is a pair of page ID and slot ID, right? And whenever you want to find this tuple, you can just follow this RID and find the corresponding tuple in your heap file. Now you can actually group everything together, and that's give you the cluster B+tree, right? So in this case, you are going to put the actual tuple inside the leaf node. And essentially, whenever you traverse the tree, find the leaf node, you can already have access to the whole tuple. So of course, you can only have one cluster B tree for every single relation, because otherwise you are going to have kind of duplicates of information. You can only have one cluster B tree on a single relation. You can have multiple unclustered B tree on a relation. So today we are going to continue to talk about access method. We are going to talk about a hash table, and then we are going to move one layer up to talk about how should you implement a whole bunch of relation algebra operators using the access method that we talk about. Okay, hash table. So I think everyone here should have already have some understanding about what hash table is, but let's just refresh our memory. So the fundamental question we want to understand is if you're asking for a point query, that is, I want to say this attribute equals to that. Okay, I'm trying to find a point in the space. Can we do better than b plus 3? So hash table is one way for you to do it. Essentially, you need to specify a hash function, which is going to map every single object in your relation. For example, here you have 4 objects in my relation, each one of them corresponding to an integer, which is age, right? You map each of these objects to one of this bucket. Okay, so assuming in total you have n buckets, right, in your system, a hash function is a function that takes as input each object, here's the integer, and output that. And output the ID to the bucket. And then you are going to put so one property we kind of want from the hash function is if you give me 2 objects that are different, if you give me 2 keys that are different, like that equal to k2, that will imply highly likely they are going to be mapped to different buckets, right? So that is the property that you kind of want to enforce. Of course, there are other properties. Sometimes you want that to be truly random, so on and so forth. So here, right, so once you have the hash function, I'm going to calculate the hash value of each of this object and put them into the corresponding buckets. And then, of course, sometimes 2 objects are different, going to be put in the same bucket, and we are going to talk about how to deal with that later, right? So on and so forth. And then within each bucket, along with the key that's being put into this bucket, you also store the RID, which is a page ID and slot ID that allows you to actually trace back to the original heap file and find the corresponding tuple. So this is a hash table. So here, your whole relation is stored in hash drive, right? And the whole hash table, which contains a whole bunch of buckets and their corresponding keys and RID, is fit into your main memory. Okay. So this is a very simplistic view of a hash table. The real world application is actually more complex, right? So you could have collision, that is, for example, 2 objects being hashed into the same bucket, you need to deal with it, right? So essentially there are 2 fundamental questions we need to understand. The first fundamental question is actually how to design the hash function. And the second fundamental question is how to deal with collision when 2 different objects being hashed into the same bucket. So for the first question, we are not going to do going to go really deep into this because there are decades of research about how should you design a hash function, right? So there's different property you want, and you need to kind of balance between the theoretical property and their practical behavior and also their performance. Okay? So here are just 2 very, very simple hash functions. If you are doing integer, right? So one thing that is really easy to do, right? If you want to hash x, which is integer, you do ax plus b and you mod p is a prime, right? You can do that for string, right? You can actually first translate the string into an integer, right? So and then you do the same thing. So all of these are kind of very simple hash function. I'm not sure any real system are using any of this, right? So in practice, there's a whole bunch of hash function that people keep studying over the years, right? So you can see this like 5 different examples, and every single one have different, essentially, performance profile. And sometimes it's even a function of the key, right? So for example, for some of the hash function, for example, farm hash, right? So like you can see when the key size equals to 32, right? So it performs really well, but if you have a larger key, it's kind of slower, right? And then faster, slower, faster, something like this. Like on the other hand, there are some hash functions that's going to be relatively stable, right? But of course, the peak performance kind of like lower compared with some other like hash function, right? So there's a whole bunch of considerations that you need to have when you design a hash function, right? So that's a function of your data type. That's also a function of how large your key is, right? So each one of them have different behavior in terms of the randomness, independence, something like that. So the bottom line is there are multiple hash functions that you can use inside a database, right? So usually as a user, right, so you don't care about those, right? You trust database to do the right decision. But when you are building a database system, right, that's one decision you kind of have to make. So we are not going to do a deep dive here, right? Yeah, but just remember, right, the choice of hash function is not trivial at all. So we are more interested in the second question, actually. Assuming you give me a good enough hash function, right? So how can we deal with collisions? That is two different objects being mapped to the same bucket. So there are so many different ways to do it. And there are actually two lines of research here. The first line deal with a method called closed hashing. So this is when we actually know how many elements that we are trying to index. And the second line is called open hashing, which is the fundamental approach that I have no idea how many objects I'm going to index, right? So I kind of need to keep it open, right? So we are going to look at one example for each line of work. So let's start from closed hashing. Here we actually know how many elements that you want to hash. One approach there is called a linear probe, right? So which is very, very simple. That is, if there's a collision, right? So then I try to find the next empty slot and then put my object there. So in this example, right? So assuming the orange one being mapped to the first slot, the blue one being mapped to the third slot, and all the rest two tuples, the green and the purple one, right? They all map to the same bucket as the blue one. So now I want to hash the green one, right? So what would happen? What's going to happen is you are going to try this bucket, and then you're going to say, there's actually something there. So I actually try to find the next one, right? If it's empty, I will put this object there. Similar for purple, right? For purple, I'm going to try this bucket. The bucket is full, right? I try the next bucket, it's also full. So I try the next bucket. So this is linear probe. It's actually very simple, right? Whenever there's a collision, I try the next bucket. So let's look at one example, right? So then it's become more clear about what it's trying to do. So there are three different type of operation you can do when you're talking about this. You first insert, right? For example, we first insert one. So I think so here's linear probe, right? I mean, if you are curious, I mean, try other probing like approach, right? So here we want to hash the integer into 28 bins. Okay. So assuming I have integer 1 is going to be put into the first bucket, it's empty, so I'm happy, right? And then I try 5, which is also going to be empty, which I'm going to be happy. And then I try 30, right? Because I only have 28 bins, right? So I think 30 is going to be hashed into maybe this bin, I hope. Oh no, sorry. Yeah, going to be hashed into this bin, right? So as you can see this bin is full. So 30 is going to try the next one, right? Being hashed here. And then if I try 31, right? So it should be hashed into this bin, but this bin already full. So it's going to be put into the third bin. Okay. This linear probe. And I try 3, for example. And for linear probe, right? Sometimes you are going to try a whole bunch of things. For example, if I insert 2, it's going to be hashed into this bin. It's going to move here, move here, move here, move here. Okay. Simple, right? So when you try to delete keys, that become a little bit trivial. Well, sorry. I mean, that become a little bit non-trivial. Yeah. So like you cannot just delete the key from the bucket. Why? Because whenever you are doing lookup, right? So you are actually, for example, if you want to find 2, right? So you need to first go to this bin, then you keep following the chain, right? So otherwise you are going to potentially miss some of the keys. When you delete stuff, you cannot just delete the key. You need to replace it with a special marker called delete to make sure when you do the lookup, you know that, okay, so there was a key here. I need to continue to follow the chain. Okay. So here, for example, if I delete the key 3, okay, delete it. I'm going to try to find 3 and then put a special marker here. Why? Because when I try to find 2, okay, so what's going to happen is you are going to find 2, go to this bucket, then you are going to say, this is now 2, but the next element is non-empty, right? So potentially 2 could be here. It's not here. I go to next one, it's a delete marker, right? So I know, okay, so there was a key here. So I need to follow this, go to the next one, then I go to next one, then I find 2. Okay, if you put this stop into empty, the search process is going to stop here because it's empty. Okay, so and then you will never find 2 anymore. So essentially, we'll delete a key from the hash table. You need to put a special marker here to make sure all the other queries knows that there was a key here. Okay, so that's very important. This is probably the only tricky part about linear probe. Okay, so what is the complexity of linear probe, right? When you try to search and when you try to insert elements. So the worst case complexity, as we can see, is actually pretty bad, right? Hypothetically, you have a very bad hash function, right? So that map all the objects into the same bucket, right? So, and then, well, what would be the worst case complexity, right? So here, I mean, of course, right, for every single element, right, in the worst case, I need to probe number of buckets equals to the largest size of the cluster, which would be my whole data set, right? So for a really, really bad hash function, that could be the case, right? So that's one limitation of linear probe, that is really sensitive to the hash function that you are using, and we really hope it has a good property in terms of the randomness of the hash function. But in expectation, given a reasonable hash function, linear probe is actually very, very powerful. Linear probe is actually kind of one really early algorithm people are doing in like 1954. People tried this idea, right? So in 1962, right, Donald Knuth actually proved it in expectation. If your hash function is truly random, right? So in expectation, linear probe take O1 time for lookup, right? Given the hash function is truly random. But of course, in practice, the hash function we are using might not be truly random. And over the essentially half a century, right, people have been working on a whole bunch of results, try to understand different property of the hash function and how linear probe going to work like under that assumption. So it's a very interesting line of work that dates back to half a century ago, right? But one thing that we just need to remember, at least for this course, is that if you give me a hash function that's not too bad, okay, in expectation, linear probe is very, very powerful. Okay, it's only need O1 time for lookup and also for search. So in practice, if you give me a hash function that's reasonably good, so here we are not going to define what we mean by good. You just trust me, okay? So there's a very precise definition about what good really means, okay? We are using linear probing in a hash table of size m that is contains n keys, n equals to lambda times m, right? Lambda is a filling factor of your hash table, which means that how many buckets are actually filled, right? So the average number of probes that you need for an unsuccessful search or an insert is this, and the number of probes that you need to do for a successful search look like this. So we can actually fill this in, like we can try this, like fill in different constant for lambda, which is the filling factor, right? So what this tells us is that assuming you give me a hash function, like a hash table that is 50% full, okay? When lambda equals to 1/2, okay? So the number of probe that I need to do is in expectation 1.5 probes for successful search and 2.5 probes for unsuccessful search. It means that if your hash table is 50% full, in expectation, okay, I only need 1.5 probes, right? So most of the time, maybe a single probe will bring me there, but in expectation, I will never go crazy, right? So I have a very small constant as my expectation. So in practice, that can be very, very efficient, right? Because if you are thinking about a hash table, right? So if you have 1.5 or 2.5 probes, highly likely all those buckets are actually fit into a single cache line, right? So whenever you are bringing that bucket to the like from the DRAM to your register, right? Sorry, yeah, like for example to your register, highly likely, right? So the same cache line will at least be in the L3 cache of the CPU, right? So whenever you are talking about 1.5 probe, 2.5 probe, right? So highly likely they are actually in the same cache line. So that's something really powerful about linear probe. So the potential disadvantage here is linear probe, as we see, is very sensitive to the hash function. You really need to have a reasonably good, good hash function like for this. And there are a lot of techniques try to improve it, right? So we are not going to go to detail, right? So there's actually half a central research about how to improve linear probe. So compared with linear probe, there's another line of research try to deal with collision, and that is when you are dealing with open hashing. That is, I don't know how many elements that I'm going to hash, right? So my hash table need to grow in an unbounded way. So there are so many different ways to do here, right? So, and here we talk about one way, which called chain hashing, which is very, very simple. So what do, right? So essentially, if multiple keys fall into the same bucket, you create a linked list to link them, and that's it. Okay. So here, for example, the blue one go to the third bucket, the orange one go to the first one, and the green one go to the third bucket. You just create a linked list, right? So the purple one go to this. You just have a linked list to link everything together. Okay. So you could do this. It's very, very, very simple. So let's look at one example to make sure we understand this. So for example, I insert 1, right? So I have 12 buckets. If I insert 1, it's going to go to the first, the second bucket, right? So I do this, it's empty. So I have a linked list from empty to this. And then I insert 5, it's an empty bucket again, right? And then I do 14, right? Which is going to fall to the first bin and then create a linked list to link them together, right? So it's very, very simple, right? I do 15. Let's do more, 3, and do 2, right? That's it. And when I delete things, right? So it's actually much easier than linear probe. I can just get rid of the key, right? So I don't need to replace it with a marker, right? So I can just delete that item from my linked list, right? So if I remove 3, here's what's going to happen, right? Yeah, and you keep the bucket empty. And really to find kind of a key, right? What you need to do, you go to the right bucket, and then you kind of traverse the whole linked list. Okay. So for example, if I try to find 27, yeah, you go to the bucket, you traverse the linked list. Here you will not find it, then you are fine. Right. Any questions? No? Okay. So what is the complexity here, right? So here is actually much easier to analyze compared to linear probe, right? So assuming you have a hash function that's truly random, right? What is the expected size of the chain for each bucket? So in this case, assuming you have m data points and n hash buckets, right? So in expectation, right? So the size of the chain per bucket is m over n, right? If your hash function is truly random. So that means that in expectation, if your number of data points m equals to on, right, in the order of n equals to the kind of number of buckets, right? So the expected length of the chain is O1, right? So every single search query is going to take in expectation O1 amount of time. Okay. So this is about the hash table, right? So any questions? Okay. So in practice, right, so you can do a lot of fancy things to build index, right? For example, there's a paper in like 2018, right, a couple of years ago, talk about essentially learned index, right? So what is the high level intuition here, right? So we talk about kind of index is pretty much just a function, right? That really map some of the condition to an ID of the tuple, right? So you could just treat it as a function and learn this function as some machine learning models, right? Like a higher order polynomial, right? So, and then you can, there are so many things that you can actually play with, right? If you take that view, right? So like just get some intuition about why that could even work, right? So if you think about B plus tree, a very interesting property of B plus tree is the query time is independent of the data distribution, right? It doesn't matter what your data looks like, right? So you always have a B plus tree of a very similar size. However, if you treat that as a function, right? So you could learn a whole bunch of things from your actual data distribution. For example, if I have a database where the key is very beautiful, like 1, 2, 3, 4, right? So, and then potentially, right, like your function f can be stored in a very compact way, right? Your fx equals x, right? So will be a very perfect index for this table. However, for B tree, it will not realize that, right? So that is actually the gap between a data aware type of index and the data agnostic type of index. So, and the goal of this learned index learn work is really try to fill that gap, to really learn the structure of your data, such that if there is some pattern inside your data, I can take advantage of it. There are a lot of exciting research that we can do here, right? So we are not going to go to detail in this course, but just remember building index is something that we have been doing like since half a century ago, and we are continue to do it, right? Okay, this is about access method. Now let's go one layer up, right? So now, given a relation inside my hard drive, I have a whole bunch of ways to access information there. I can do sequential scan, I can do index lookup, right? So I can do index scan, right? I can have hash table, have B plus tree, right? So now let's try to implement a whole bunch of relational algebra operators using those access methods. So what do we want to implement? We want to implement things like join, like projection, right? Like select, like sorting, right? So on and so forth. Whole bunch of operators using the access method that we just talked about. So the interface we want to provide to the upper layer, yeah, it's really a higher level of abstraction, right? So even higher than access method, right? So we want to expose the relational algebra like the relational algebra operators to my query optimizer, such that everything above it will actually not use the access method. Will actually tell me, okay, here's relation 1, here's relation 2. I want to do this relational algebraic operator. I want to R1 join R2, right? And then the database is going to say, now let me use this this access method, and this access method is going to talk to the buffer, right? So you can have a very beautiful layered structure of the system. So let's talk about this. So the first operator that we want to do is a very simple one. We want to support the select operator, right? So the input of the operator is relation R, and then you'll have a condition C, right? So you remember from our second or third lecture, the semantic of this operator is I'm going to go through every single tuple in my relation R. For every single tuple, I'm going to check whether my condition C hold. If C is true, I return that tuple, okay? So how can we implement this? The natural way to do it, right? So I can just use my access method like sequential scan over my heap file, right? So that's one way to implement this operator. So in the book, in the textbook, so there's a difference between clustered heap file and unclustered heap file, right? So in this lecture, right? So here for this example, let's assume it's a clustered heap file. That is, all the pages are kind of stored together. And all the tuple actually stored together. Whenever I do it, it's a sequential scan. Okay. So what should we do? We bring page from hard drive to DRAM one by one. For each one of them, I scan all its tuple, and I check whether predicate C is true or not. If it's true, I output the tuple, and then continue to do this. I mean, as you can see, it's very simple. Okay. So what is the I/O cost of this? So essentially, assume you have relation R as input, and assuming you have R tuples, okay, in this, and then assuming you have BR pages, to store relation R on your hard drive. So essentially, assuming you have a buffer with m pages, and so like remember this notation, we are going to continue to use it. What is the cost to read R, right? So essentially, for every single page, I have one IO, right? So essentially, if I do sequential scan to implement the select operator, I'm going to have the cost to read the data as BR, number of pages. How expensive it is to write down the result, right? So here we have a key constant called selectivity. So here called alpha. Alpha take as input your predicate, the C, and your relation R, and output the percentage of tuples in R that satisfy C. Okay. So that's selectivity, right? So if alpha goes to 1, it means that every single tuple in the relation satisfies the predicate and will be in the output. If alpha equals to 0, it means that none of the tuple in the relation satisfies the predicate, so your output will be empty. Okay, alpha is something between 0 and 1. It's selectivity. So what is the cost to write down your result, right? So here, how many tuples are we going to have? I'm going to have alpha times R number of tuples, right? How many pages those fit in, right? So we are talking about alpha times BR, right? So this is the number of pages I need to hold my output, right? So essentially in total, right, when you are doing this stack operator, the total cost, both the input and output, right? So it's going to equal to BR, the number of pages in the relation, plus alpha times BR. Okay, makes sense? In real-world database systems, it has a very similar cost model, but it's going to become more complex. For example, every single time I read a page, I have a different cost compared with writing a page, right? And every single time I read a page in sequential scan, it's going to have different cost compared with reading a page in random access, right? So in real world database systems, this cost model and this formula, so in a real world database system, like this formula is going to be much larger than this one, even for sequential scan, a single like operator is going to have the sequential read, sequential write, random read, random write, right? At least 4 terms, so in this cost model. Okay, so by here, right, so we just talk about at really high level, right? If you just count how many IO you are going to have, right, it's equals to this very simple formula. Okay, so the point is, database is going to have all those cost model for every single ways to implement the same operator. And as a user, when you write a SQL query, right, you'll never tell the database, you should use B-tree, you should use sequential scan, right? It is database's job to really pick the best implementation for each of those operators and also for your whole query. That is why database need to have this cost model, right? And then to really facilitate the process of picking the right implementation for you automatically. So you can also implement the select operator using index. And then that actually depends on what type of predicate you are giving me. For example, when your predicate C checks for equality or smaller than, larger than, right? Then and assuming you have a B-tree index over my relation, right, on the same attribute that C is checking, then you could do index scan using B-tree to do this select operator, right? So assuming you have an unclustered B plus tree index for that is able to answer the predicate C. So what you are going to do, you are going to find the right leaf node by traversing the tree. Then you scan the index from left to right, or from right to left, right, depending on what predicate you have in C. And then you try to fetch the corresponding tuple in the heap file and return them. Okay. When you have an index that is consistent with the predicate C, you could actually use that to implement the select operator. So what is the IO cost here, right? So here, assuming R has R tuples and has BR pages, right? Assuming how buffer like this. So in the worst case, right? So what is the time you need to find the right leaf node, right? So that is the kind of the height of the tree, right? It's log R. And then you, what's the time for you to fetch the tuples, right? So here, because you have an unclustered B plus tree, in the worst case, every single tuple that you fetch might be in a different page. right? Because even though the key is just sorted inside my leaf node in B tree, the tuple can actually be scattered around, like all over the place. I don't really have control there. In the worst case, every single tuple you fetch in my heap file can give you an additional page IO. Okay, so essentially in the worst case, the cost you need to fetch the tuple equals to the selectivity R. As you can see, the selectivity is always there, right? So it's kind of it's a key constant inside database. Now we are going to talk about how to estimate alpha next week. Okay, so you have selectivity R times number of tuples in R. Sorry, selectivity of R and its predicate, right? So and you take 2 input alpha multiplied by how many tuples in R. That is the number of tuples you need to fetch. And for every single tuple, in the worst case, you will incur 1 page IO because they're in different pages. And again, right, so number of like the amount of time you need to write down the result equals to alpha times BR, right? That's the selectivity. The total cost look like this, right? So the first item, right, log R is the time you need to find the right leaf node, and then for the second term is the time you need to fetch the actual tuple, and for the third term is the time you need to actually write down the output. And similarly, if you have B tree, right, you can also use it. You find the right leaf node, then you scan all the leaf node, you fetch the right tuple right away, right? You do not need to go to the heap file because you don't really have it here, right? So, and then assuming R has R tuples and BR pages, right? What is the cost, right? Again, right, finding the right leaf node is log R, right? In the worst case, the time you need to fetch tuples, right? So this term become kind of smaller because I do not need to fetch all the original tuples, and I know all the tuples I need to fetch, they are actually stored together, right? So essentially, if my relation has BR pages, I need to fetch alpha times BR number of pages, like which will contain my result. Similarly, to write down the result is alpha times BR, right? So in total, you have something like this. So if you put them together, right? So now we introduce 3 different ways you can use to implement the same relational algebra operator. You can do heap file scan, you can do unclustered B plus tree, or you can do clustered B plus tree, right? If you compare this, right, you can see they actually work better for different scenarios. First one, for the last term, for writing down the result, is always the same, so we just ignore this. So to compare these 3, you are comparing with actually sequential access of the whole file, compare with a random access of log R number of files, right? And also you are like you compare essentially like unclustered and clustered, right? So here you can see the difference. For unclustered B plus tree, in the worst case, I need to access alpha times R number of pages, and for cluster B plus tree, in the worst case, I need alpha times BR number of pages to fetch the tuple, right? So if you plug in the constant, right, so you will actually know which one will perform better to implement, as one implementation of this operator. Okay, so as a user of a database, you don't care how the database is doing this for you, but underneath the cover, the database is going to have a cost model for each different ways of implementing this, and then it's going to plug in the constant, right, and then pick the best one for you. So that's why database is so easy to use, because it's going to manage all those complexities for you as a user. So at a high level, right? So when we use each of these access methods, like each of these implementation, it depends on different factors, right? Depending on the relative speed of sequential access and random access, right? When we do sequential scan on a cluster heap file, it is like very large sequential access, right? But when you're doing B tree, there could be some random access, right? So the relative speed actually matters. The selectivity also matters, right? So for example, here, when alpha goes to 1, as you can see, using unclustered index will actually be slower, right? Because you're better off just scan the file and return everything to me, other than fetching every single tuple that's scattered around in my heap file, right? So it's not often the case. I mean, it's not always the case that using an index will pay off, right? So the selectivity is also a very key constant when you are making a decision on which one to use. And also it matters a lot whether the index is clustered or not, right? So all these factors, to balance those factors at the database's job, is not your job as a user, right? Database is going to automatically pick the fastest one, giving an estimation of those constants. Right? What's important is database only knows the estimation of, for example, selectivity. It may make a wrong decision, right? But at least it will try to make decision for you. And it is often the case that they are not that wrong, okay, in modern database systems. Okay, so this is the first half of the lecture, right? So let's take a break. When we get back, we are going to talk about how to sort tuples inside a relation. Yeah. So if you have any questions, I'll be here to answer them. Okay, so let's continue. So we talk about the one operators in the first half of lecture. That is how to do essentially 3 simple ways to do select, right? So there are other relational algebra operators, and we are going to continue to talk about those. So one operator that's interesting is sorting, right? So essentially, you have relation R and you have an attribute A, and then essentially you want to sort all the tuples in this relation R according to the attribute A. So if you have a cluster B tree built on A, you are very lucky because what can you do? You just scan the leaf page from in the B plus tree and you are done, right? Because when you have such kind of a B plus tree index and when it's clustered, right? So all the leaf node will already give you all the tuples arranged in that order, right? So what's interesting is assuming you do not have that, right? So for example, if you only have unclustered B plus tree on A, right? So that's going to be very slow because I can scan the leaf node to get the record ID, right? However, when fetching every single tuple, right? So in the worst case, I'm going to have essentially one random access per tuple because they could be stored in different pages, right? So the whole thing will become very, very slow, right? So what is the IO cost if you do this, right? So because I mean it's going to be equals to like number of tuples, right? So that is your IO cost, right? And every single IO is a random access that's going to be extremely slow. So the fundamental question that we want to understand here is how to sort tuples on disk. So everyone here must know quicksort, right? So what's the reason that we actually will not use quicksort for this purpose? It is because when you are thinking about quicksort, the underlying assumption is I can actually access things tuple by tuple, right? I want to minimize how many times I'm going to compare two attributes or two tuples. But here, because every single time I access a tuple, I'm going to bring in the whole page, right? So quicksort is simply not designed to be IO efficient for essentially block access storage. So that is why we kind of need a new algorithm for this to really optimize for IO instead of optimizing for number of comparisons you are going to have in your algorithm. So the algorithm we are going to talk about is something we call external sort, which just means we use external storage, here the hard drive, to sort it. So assuming you have n pages on disk to sort, and assume you have a B page buffer. So that is always like our assumption. So there's a simple case, right? So assuming n is smaller than B, right, in the sense that your buffer is much larger than your data, okay? In that case, the whole thing is easy to do. So what should you do? You load all the data from the hard drive to the buffer. Because your buffer is large, you can actually hold all the data. You are going to incur essentially one part of reading of the data as your IO cost, and then everything in the buffer, you do quicksort, you're done. Okay, when your buffer is large enough, to hold your data, it's very easy to solve. The case that we are interested in is when your data is much larger than the buffer, which, to be honest, arguably is often the case in a database system, and also what makes that interesting, right? So when your data is much larger than buffer, B larger than B, what can we do? In this case, we cannot load all the data from the hard drive to the buffer because the buffer is not large enough. So the external sort algorithm, it depends on a very simple intuition. Okay, that is, if you have two files that is already sorted, for example, I have file 1 and every single tuple here is already sorted. I have file 2, every single tuple here is already sorted. If you want to sort these two files, right, I only need a 3-page buffer. So this is actually very, very simple, right? So what should we do, right? So we read 1 page from the head of file 1, from hard drive to my buffer. I read the head of file 2, and then I have 2 pages in my buffer. and I compare the beginning of these 2 pages, and I pick the smallest one. So here, 1 is smallest because I'm comparing 1, 2, right? 1 is smallest, I cannot output 1 to my output buffer, that's my third page. And then I move the tuple up, right? And then I keep comparing the height of these 2 pages. And now the 2 is the smallest one, right? So I output the 2, I move 3 up, I compare 3 and 4, I output, essentially now my output buffer is full, I just flash it out to my hard drive. I keep doing this, it's 3, it's 4, right? And then my output buffer is full, I just flash it out. And then I keep reading file 1, reading file 2, right? So I continue to compare the height of the buffer. So here you have 5 and 8, I output 5. I move up 6, I compare it, oh, it's also 6, it's smallest. I do this, my output buffer is not full. You do this, right? And you move 8 and 8 here. So as you can see, right? So with only 3-page buffer, I can actually sort 2 files, given that they are already sorted. So the whole sort algorithm we are going to talk about relies on this very, very simple observation. Essentially, I decouple the algorithm into 2 different phases. In the first phase, I'm going to do sorting. I'm going to partition a very large file into a whole bunch of small chunks, and partition them in a way that every small chunk fit into my main memory. Then I will bring every small chunk to my main memory, and I just using, for example, quicksort to sort them, and then I flush them out. And now I have a whole bunch of small files. Each one of them is already sorted. And then the second phase is merging. We want to combine all those small sorted chunks into a larger file using this very simple observation. So here's just one illustration of that. Assuming I have a whole bunch of files on my hard drive, I have n pages to sort, and I only have a 3-page buffer. Okay. So what should we do? I bring in 3 pages to my memory, and I sort them, and I flush them out. I keep doing this. I'm going to have a whole bunch of small files. Right? Every single small file contains 3 pages because that is what I can sort in memory. And then I have a whole bunch of small files. Each one of them is already sorted. And then I'm going to merge them. I'm going to, for example, take the first 2 files. I will merge them using my 3-page buffer. And then I get a larger file, now contains 6 pages, and sort it, right? And then I take this 6-page file and then merge that with another small file. I keep doing this. I will end up with a very large file that is sorted. So it's a very, very simple algorithm. So how expensive that could be, right? So here we are using a 3-page buffer, right? But assuming you have n pages on hard drive and you have a b-page buffer, right? So in the sorting phase, so what are you going to have? You are going to have n over b number of runs, right? So each run is a kind of small chunk, right? So you are going to partition this n pages into n over b number of chunks, right? Every single chunk will fit into my buffer because I have a b-page buffer. So for every single run, I need to read all those files, like all those pages in that chunk to my main memory, do the sorting, right? So essentially I need to read n pages in total. Also, I need to write out the result. So I'm going to write n pages in total in the sorting phase. After the sorting phase, I have n over b number of small files. Each one of them contains b pages and sorted. And in the merging phase, right? So with the 3-page buffer, I can merge 2 files. Actually, with a b-page buffer, you can actually merge b-1 files, right? In the same pass. So essentially, the merging phase, you actually count how many passes you need to merge them, right? So essentially, you actually need log b-1 and n over b number of passes for merging, right? So you can think about this as a tree, right? So you merge this once, you merge it twice. What is the depth of the tree, right? So because the fan out is b minus 1, right? So the depth of the tree is actually log b minus 1 and n over b. So how much I/O do I need to pay for every single layer of the tree, right? Essentially, every single time I do merging, I need to read all the pages in my file and also need to read them out, right? So I pay n pages read and n pages write for every single pass, right? So in total, this is what you have, right? So essentially, how many read and write passes I need to do over my file in total is going to be log n over b plus 1, right? So this one is what you pay in sorting. This log term is what you pay in merging, right? And for every single pass, I read and write n, and that's it, right? So this is actually my I/O complexity, right? So it's not the computational complexity, but this is the amount of I/O I need to pay to do external sort. So as we can see, this is actually very powerful because in general, when B is reasonably large, this log term is actually very, very small, right? So actually to sort a really large file is actually not, I mean, it's very challenging as we'll see, right? But it's not that desperate, right? So I mean, and there are some reasonable way you can do to do it. And another thing is, assuming you have a buffer B is larger than the square root of n, that is your buffer is not that small, okay? Assuming you have 100 pages, then you have a 10-page buffer, right? So in that case, the whole merging phase can be done in a single pass, right? So in this case, if you have a reasonably large buffer, B larger than square root of n, right? The whole thing can be done in just 2 passes, okay? Your sorting phase will read and write once, and your merging phase will read and write once. So that is the power of external sort. In practice, right? So people have been doing this for decades and decades. So there's actually one benchmark just to like people can actually compete in, right? To actually like try to understand essentially how fast we can sort terabyte of data, right? So in a modern type of sorting system, right? So this is actually something from 2016, right? So people have all those distributed sorting type of thing, right? So essentially partition the data into different nodes. Here, I think there's a 512 machines, right? And then for every single one, you can see there's a whole bunch of different sorting algorithms, right? So at the end of the day, you often have the merge and sort, like that type of thing that we talk about, right? But this is what essentially modern sorting system look like. And it's way more complex than what we have been talking about. But the algorithm we have to talk about is actually a very powerful building block that people often use, even in those state-of-the-art kind of sorting systems over terabyte or petabyte of data. Okay, so this is about sorting. So now let's talk about another operator, right? So that is join, right? So probably which is kind of the holy grail of relational algebra, right? So I have 2 relations, I have to join them. So let's consider theta join, right? So theta is the predicate, right? So essentially, what's the semantic of this one? I take one tuple from R, I take one tuple from S, I evaluate the theta over R and S, and then if that's true, I return this pair. Otherwise, I move on. Okay. So the easiest way to do this is called nested loop join, right? Which has a very simple algorithm. That is, for each tuple R in relation R, you check every single tuple S in relation S, and then for each pair, you are going to check theta. If it's true, you output the pair. Otherwise, you continue this for loop. So this is almost a definition of this join operator, right? So specifically, if you have R and S, what you are going to do, right? You are going to take the first tuple of R, and then you scan S. You take the second tuple of R, you scan S. The third tuple, you scan S, right? So this is kind of a very simple algorithm to do this. So what is the cost? That actually depends on how large your buffer is, right? So assuming you have a small buffer, you have 3 pages, right? So then what are you going to do? You are going to have 1 page to store R, you have 1 page to store S, and you have 1 page to store your output, okay? So in that case, what is the I/O cost of nested loop join? So essentially, you are going to have one term, which is the number of page of R, which is the which is the outer loop, right? So you are actually sequential scan R. You for each tuple, I need to bring that from hard drive to memory, right? So it's one pass of sequential scan. So I have a BR in the first term. And then for every single R, I'm going to sequential scan S. Because I only have one buffer to store the information of S, I'm going to pay number of tuples in R multiplied by number of pages in S. That is my total IO cost. Okay, for next loop join with a very small buffer. And also this formula ignores the IO to write the result out, right? So that's always the same, like across everything we are going to talk about at this moment. So we are just ignore that term. Okay. So another thing that's interesting, which is going to kind of keep getting back to us, is the join order actually matters, right? So here, as you can see, is a nested loop. So which relation should I put in the outer loop? Which relation should I put in the inner loop? It actually matters, right? If you put R in the outer loop, this is your cost. If you put S in the outer loop, this is your cost, right? So you have the sequential scan, you pay that for S, and then for the inner loop, you pay this. If you compare these two, right? So they actually is different. So which one will database want to use if it can only choose between these two, right? Like to optimize for the join order. In this case, it's actually you want to put a smaller relation to be the outer loop, right? So essentially, like this term, the second term, R times BS and S times BR is going to be the same, assuming the tuple size is the same, okay? They are roughly at the same scale, right? So essentially, you are optimizing for the first term. So essentially, right? So if database must pick between these two, which fortunately will not be the case, but assuming database only have this choice, when it optimize the join order for nested loop join, right? It is often the case that it wants to put a smaller relation in the outer loop. And again, it is database's job to deal with that for you. Okay. So just as an example, right? Assuming you have relation R has 1,000 pages, has 100,000 tuples, and you have relation S with 500 pages and 40,000 tuples, for example. So the cost of doing R join S, putting R in the outer loop, right, is going to give you like 50 million IOs, right? Something like that. If you do the other way around, putting S first, you are going to pay, for example, 40 million IOs, right? Both of them will be very, very slow, but the second one will be faster than the first one. Okay. So what would happen if you have a larger buffer, right? So how can we take advantage of that? In this case, when you have a very large buffer, for example, your buffer size M is larger than the number of pages of S plus 2. In this case, right, so I can actually cache my whole S into my buffer, right? So essentially for all the inner loop, I will not pay an IO other than the first time I bring S into the into the system. So essentially here the IO need to pay, right? When you have a very, very large buffer that is larger than a smaller relation, you are going to pay an IO cost, which is BR, number of pages in R, plus the number of pages in S. Okay. So here, right? So which one you want to put in the inner relation? That's sorry, like in the inner loop, right? So here, right, when you have a very, very large buffer, right, you actually want to put the smaller relation to be in the inner loop to make sure you can fully cache that, right? So as you can see, right? So the join order that you like is actually not only the function of the relation itself, but also how large the buffer you have, right? When you have a very, very small buffer, when you only have 3 pages, right? So you want to put the smaller relation in the outer loop. But when you have a very large buffer, but not too large, right? So have a buffer larger than the smaller relation, right? Smaller than the larger relation, right? You might want to put a smaller relation, right, in the inner loop, right? So as you can see, the optimal join order is not only a function of the relation and the predicate, but also how large the buffer is. And that is why if you build a database system to to put all those responsibility of picking the best join order to the user, you are pretty much setting the user up to failure because there are so many different factors you need to consider to make the optimal choice. So that is why database actually want to do this automatically for the user, right? When you are writing a SQL query, right, in the first half of the course, you never think about the join order. And that is the beauty of a database to really automatically deal with that for you. But as you can see, there's a very delicate trade-off, right? It's a function of the data, function of the predicate, function of the selectivity of the predicate, and also how large the buffer is. Okay. Sorry. Yeah. So fortunately, this is not the only choice we have. We can do so much better than a simple next loop join. So a very simple optimization over this is something that people call block next loop join, which is very simple. So here's the algorithm, right? Essentially, instead of enumerating every single tuple, I'm going to do that in the block level. For each block or for each page, okay, in R, for each page in S, I bring them in to my buffer, and then I'm going to scan my tuple R in that page. I'm going to scan tuple S in that page, and then I'm going to check kind of like essentially like R and theta. Okay. Oh, sorry. What is wrong? Sorry. Yeah, sorry, it's my fault. No, sorry. Yeah. Okay. Yeah. So I mean, this is red algorithm. So essentially, for every single block in R, so I'm going to bring one block from R to my buffer, and then I'm going to scan essentially. No, I'm wrong. Sorry. A little bit confused. Yeah. Sorry. I mean, yeah. So yeah, this is the red algorithm. Sorry. Yeah. So so essentially, like for every single pair of the block of R and the block of S, right? I bring them in, right? And then I'm going to scan all the tuple in that block, in R block, and all tuple in S block. I check theta. If it's true, I output. Otherwise, I don't. Right. So like in this case, like assuming 1, 2, 3 is in one page, 4, 5, 6, 7 is another page. Assuming 1, 3 is in one page, 5, 6 is one page. What I'm going to do is I'm going to bring 1, 2, 3 to the buffer, 1, 3 to the buffer, and I check the pair. And then I bring 5, 6 to the buffer. I check all the pair. Then I bring 4, 5, 6, 7 to the buffer. Bring 1, 3. Bring 5, 6. Yeah. Okay. So what is the cost here? So when you have a very small buffer, what would you have? You actually do much better compared with next loop join, right? So in this case, the first item is is what you need to bring in all the block of R, okay? And for every single block of R, you bring in the whole S, right? When you have a very small buffer, right? The IO cost is number of pages in R plus number of pages in R times number of pages in S. So assuming that you have a relation look like this, right? 1,000 pages for R, 500 pages for S, we are talking about 500 thousand IOs, right? For block next loop join, right? In this case, and compare that with the next loop join, right? That we have, which actually takes 50 million IOs, right? So as you can see, right? We are so much faster. We are 2 orders of magnitude faster, right? By simply reading this, kind of block-wise way, right? So later down the road, if you are actually going to take the advanced system lab, right? This is actually a very popular optimization you are going to see everywhere, right? So essentially, it's try to take advantage of the locality of data access, right? To really make things faster. So when you have a large buffer, right, potentially you can do even better, right? When you have a buffer of size m, right? So of size m larger than 3, to make that precise, okay? Then this is what you're going to have, right? So essentially you are going to have BS plus BR times BS over m minus 2, okay? So the first term is not BR, first term is BS. This is actually very easy to see, okay? So what you are going to do is you are going to partition S into smaller chunks. Okay, because I have a large buffer, a buffer equals M, I'm going to partition S into a whole bunch of chunks where every single chunk contains M-2 pages. And then how many partition I need to do? I need to do BS over M-2 number of chunks. I can partition S into that. For every single chunk, I do the join. Okay, essentially for every single chunk, I bring R into, I bring the whole R into my memory, right? So I'm going to join this chunk of S with that. Okay. So in this case, what I'm going to pay, I'm going to pay M-2 to, that's a cost to bring that corresponding chunk of S. I'm going to do one sequential scan on R, right? So I'm paying M-2 plus BR for each single chunk. And then I have BS over M-2 chunks, right? So essentially, if you multiply them together, that's give you this cost model. Okay. We don't have a relatively large buffer, right? So this is actually what you can do with block next loop join. And you can do even better. Okay. So yeah. So this is another example. So assuming I have an index over my relation S. And assuming I'm doing equijoin, right? So assuming here, I mean, I cannot do all the predicates anymore, right? So because my index will not support all the predicates. Assuming you are doing equijoin, right? For example, RA equals to SB, something like this. Assuming I'm doing that. And assuming I have a B tree over S, the thing you can do is you can actually use the index, right? You can enumerate every single tuple in R, and for every single tuple, you do an index step. Right, so if you are doing equijoin, you actually try to find all the tuples in S whose attributes equals to something, right, which is a function of the R. Right? And then you output all the pairs, and you're done, right? So what is the cost here? The cost is assuming you have a buffer, right? Essentially, it actually doesn't matter how large the buffer is anymore. Sorry. So what is the cost? Essentially, you pay one pass of sequential scan on R, that's BR, number of pages in R, plus for every single tuple in R, you do one lookup in the index. So here, assuming C is the cost for a single lookup in the index. Okay, so this is actually what you are going to have when you have an index and you are able to use it. So just go back to our old example, right? So assuming you have 1,000 pages in R and 500 pages in S. Assuming every single index search lead to, for example, 2 IOs. Okay, I mean 1 IO is the time you need to fetch the leaf node, right? Another IO is the time you need to fetch the actual tuples. Assume, I mean that's actually a pretty realistic kind of assumption. Okay, so in that case, so amount of IO you need to pay is only 200,000. Okay, so as you can see, and it's very powerful, right? Because like remember the same example when you're doing next loop join, we are talking about 50 million IOs, right? So here, right? So if you have an index, if you are able to use it, right? So we are talking about like it's more than 2 orders of magnitude and improvement on the number of IOs. And we can do even better, okay? As we will see. Another way to do join is something called sort merge join. Like again, it doesn't apply to all the possible predicates, right? But here, let's use equijoin as an example, right? So we want to join these two relations to make sure kind of RA equals to SB, something like this, okay? So I'm assuming both relations are sorted, okay? If they are not sorted, I will sort them, okay? So here R is sorted, it's 1, 4, 8, 9, S is sorted 2, 4, 5, 6, right? So then what you are going to do is you are going to scan both relations. You are going to bring one page from R, you are going to bring one page from S into the buffer, and you are going to essentially join them. You are kind of comparing the head of the buffer. So just as one example, right? So here I'm going to bring in 1 and 4. I'm going to bring in 2 and 4, and then I'm going to compare the head. So here clearly, right? So if you join 1 and 2, you will get nothing, right? Then I just get rid of the smaller tuple. And then I kind of move the rest of the tuple in the buffer up. And then I do it again. I try to compare the head. They are not the same, right? So I just get rid of smaller one. I bring the rest of the like tuple up. And then I say, yeah, now I find a pair 4 and 4, right? I'm doing equijoin, so I'm going to output it like in my output buffer. I get rid of all of this, and then I keep scanning the relation. I bring the rest of the kind of tuples from S into my buffer. Yeah, I do this. I bring the rest of R, right? I'm going to get rid of smaller one, 5, 6, there's no join. I get rid of this. I finish scan my relation, then I'm done, right? So as you can see, right, once R and S are kind of sorted, right, essentially, you can actually just do sequential scan on like on those relations, right? And then I kind of like, here's my output. So as you can see, this is actually very, very efficient, right? So essentially, assuming you have relation R and S are kind of sorted, the cost is simply one pass of sequential scan on R and one pass of sequential scan on S. If they are not sorted, you need to sort them first using the external sort algorithm that we have been talking about, and also you like sort R and you sort S, right? Which can be very, very efficient. And then I mean, there are other, you can actually do other algorithms, right? So assuming you are doing equijoin, right? So there's one algorithm you can do is something called hash join, which is very simple. You first build a hash table for R, and then you probe it. For every single tuple in S, you actually try to check whether they exist in the hash table or not. If it exists in the hash table, you output. Okay, so it's kind of very simple. So you have R and S. Assuming R, you have 4 tuples, S have 2 tuples. You first build kind of an in-memory hash table. You put every single object right into their corresponding bucket, right? And we talk about how to deal with collision, right? So you can do open hashing, you can do linear hashing, it doesn't matter. And the second phase, you probe. For every single example in S, you will check whether the corresponding object exists in the bucket or not. If you find a match, you output. If you do not find a match, you do nothing, right? So as you can see, assuming the whole hash table fit into DRAM, this algorithm is extremely efficient, right? So it's only take a sequential scan on R and also a sequential scan on S to finish this join, right? And of course, there's a whole bunch of limitations here, right? First one, you can only do equijoin, right? So like I cannot do other type of joins, but assuming I'm able to do this, and assuming the hash table fits in memory, assuming you are doing equijoin, it's very, very efficient. Of course, there's another question that is, okay, so what if the hash table doesn't fit into my DRAM, right? So in this case, there's actually one very classical algorithm called Grace hash join. It's part of a database people are building starting from 1981, right? Which proposes algorithm. It's very simple. You have a very large relation R, you have a very large relation S. So what you are going to do is you are going to partition R using a hash function H1. You are going to actually like partition them, right? Like put R into different smaller chunks. And then you partition S using a hash function H1, okay? And then you pick each pair of the partition, right? So you take the first partition of R and the first partition of S, right? So, and then you do hash join using another hash function H2, right? So here, right, so you do not need to compare, for example, the first partition of R and the second partition of S. Why? Because both of these are partitioned using a hash function H1. So there can only be kind of matches between the first partition of R and the first partition of S. Now you do not need to check all the pairs. You only for example, if you have like n partitions, you need to consider n pairs. Okay. So as you can see, this is very, very efficient, right? So what is the cost? Essentially, to do the partition on R, I need to read R, build a hash table, right? So I do not need to build a hash table actually. So I'm going to read R for every single tuple. I kind of hash it into a bucket, but because I only cover partition, right? So I can directly map that using the hash value into one of these partition. I just write it out. Okay, I read one, hash it, and write it out. Okay, So essentially the partition phase will be one read and one write. Okay, so that's 2 units of BR. And then for S, that's the same. And then when I do the join, do the hash join, right? So essentially I only need 1 pass of R and 1 pass of S, then I'm done, right? So essentially if you're doing this, I'm paying 3 units of BR plus BS if you only count IO, okay? So as you can see, it's very efficient. Here, all the assumption we need is you are doing equi-join, right? If you are doing different type of join, there's nothing else I can do. But if you are doing equi-join, right, I can actually do Grace hash join and give you an algorithm that going to finish with 3 times BR plus 3 times BS. Okay. So we talk about 2 algorithms, right? So I think the most powerful one is probably the Grace hash join and the saltmerge join. And we can actually compare this. So let's get back to our kind of example, right? So I have R with 1,000 pages, I have S with 500 pages. So if you just plug in the cost model, right, assuming the buffer size is 100, for saltmerge join, like roughly I need like 5.8 thousand IOs. As you can see, this is amazing, right? Because when we are talking about next loop join, we are talking about 50 million IOs, right? But if you are able to do saltmerge join, so we are talking about 5.8 thousand IOs. When we talk about Grace hash join, in this case, we are talking about like roughly 4.5 thousand IOs, right? So in this case, right, so assuming the read IO expensive as write IO, because that is our cost model, right? And assuming IO is the only performance bottleneck, which often is not the case in real system, but assuming this two is true, right? Database would pick Grace hash join for this, okay? So this is just the type of exercise that data optimizer do automatically, right? To really compare all the possible algorithms, right? And pick the best one for you. And the way the database do it is to make sure it has a kind of realistic cost model. I mean, it's cost model, right? So sometimes it's not precise, but have a realistic cost model that's good enough and compare different approaches for you automatically. And of course, right? Sometimes database might actually favor saltmerge join, right? So here's just some examples. For example, I mean, sometimes your data is already sorted, right? So you actually do not need to pay kind of the cost for sorting them, right? So in this case, saltmerge join is often faster. And also maybe there are other operators that need the data to be sorted anyway. In this case, maybe you favor saltmerge join, right? So, and also we need to deal with some predicate that's actually not equi-join. For example, if you have smaller than, larger than your join predicate, right? So here I don't know how to do hash join, right? I can only do saltmerge join, right? So here you have the constraints on which algorithm that you could apply, right? So that will also change essentially how you do this. So just to put everything together, right? So this is we talk about a whole bunch of join algorithms, right? So we talk about next loop join, the block next loop join. They are very slow, but the good thing about them is you can actually apply them to all the join predicates, right? Essentially, they don't care what join predicate you have. I bring in a pair of tuples, I evaluate the predicate, I'm done, right? We talk about index next loop join, right? Which actually can support whatever predicate you can support in your index, right? And we talk about saltmerge join, we talk about hash join, right? So they are very, very fast, but the downside is they can only support kind of a smaller collection of predicates, right? For hash join, right? In most of the cases, I only know how to do equi-join. For saltmerge join, I can extend that to equi-join, to smaller than, larger than, right? So when putting everything together, you can see, even for this very simple operator, join operator, there are so many different things I can do, right? So, and if you just ask the user to do this for you, right, you are pretty much setting the user up to failure. Right? Why we need a database system is we want to pick this automatically for the user. Okay, so as last part of the lecture, we talk about join, right? The different algorithms. You might have the impression that join is a problem that's already solved, right? Which is actually not the case. So we are not going to go detailed here, but I just want to give you one example to convince you there are so many interesting things you can do about join. Because we were talking about join 2 relations, right? But what if I want to join 3 relations? For example, I have a query that I want to join RAB, SBC, TAC, right? So in this case, so it's very interesting because this is actually corresponding to funding triangles in graph, right? So here's actually how you think about it. Every single entity become a node. And for example, if AB appear in R, you have one edge between them. If two node appear in S, but one is B, another is C, you have one edge S between them. If you similar for T, right? So if you are doing this join, you are doing RAB, join SBC, join TAC, right? So essentially, you are pretty much finding triangle. I want to find A, give me B, B give me C, and you have AC, right? So you're actually finding triangles in this graph, right? So which actually become very interesting because if you join them in a pairwise way, for example, you first join R and S, then you join the result with C, or you do whatever order. In the worst case, what's your complexity? The worst case complexity is going to be n squared, assuming n is the number of tuples in R, S, and T, because in the worst case, every single pairwise join is going to bring me from n to n squared. That's simply my output size. However, just a very classical result tell you there are actually not that many triangles in the graph, right? So there are at the most n to the 3/2 number of triangles in the graph. So essentially, if you do this in a pairwise way, you are actually paying way more than your actual output, right? So my worst complexity is n squared, but I know my output will not be n squared. So amount of computation there. So fundamental question is, can we get an algorithm that has complexity n to the 3/2, right? Like which is, I know is the worst case, right? So number of triangles in the graph instead of n squared, by drawing all three relations at the same time, right? So that's a very interesting problem. People have been working on this over the last decade, actually, right? And people are still making progress to really give you essentially the worst case optimal join or beyond the worst case optimal join. Right? So there's a huge area, like huge community to really try to understand this problem, not drawing relation in a pairwise way, but drawing them all together, right? So, and also for database, you can see how we can implement every single algorithm into the database system because they are just a different implementation for this operator, and you have a cost model. Right? So this is what we have. We talk about all the 4 layers. In the next lecture, we are going to move 1 layer up, and we are finally reaching query optimizer, which are going to take as input a SQL query and compile them into a whole bunch of relational algebra operators and run them. Okay, so that's all for today. If you have any questions, I'll be here to answer them. Otherwise, I'll see you guys on Wednesday. Yeah, thank you.
Hello, Professor.
Hi, hello.
Hello. I actually don't have a question, but I have an input. Maybe you could go to the triangle slide.
Yeah.
And maybe you could add the ABC into the.
Okay, makes sense.
So that
Yeah.
people could understand it easily.
Sure, of course. Yeah.
Okay. Thank you for the lecture.
Thank you.
Thank
you. Bye. Okay. So if there's no other questions, yeah, see you guys on Wednesday. Thank you.